Can you remove your name tag? It might make a noise.
All right, Jan will give our next talk on designing parallel data structures.
Okay. Hello, everyone. Thanks for coming. And before I go into any content, let's just briefly talk about the computational models where in the shared memory multi-core setting, we have work, total number of operations, span the longest dependence chain. And sometimes in our talk, I'm going to mention I/O. That means the I/O complexity or the cache complexity in the I/O models. Okay? And that's it. Okay, so what do I work on? So I design parallel algorithms on a lot of different domains like graphs, geometric problems, learning algorithms, some of just used in Julian's talk just now, and then sequence algorithms. Okay, so one common thing I've noticed is that almost all of these algorithms will use some parallel data structures, okay, which is not quite surprising because we all know data structures are important. In most of the undergraduate CS curriculum here in this country, students will first learn data structures in the freshman programming courses and then learn algorithm courses in upper division. Okay? And then in these algorithm courses, we learn the coolest ideas like abstract data type and then like priority queue. You can design algorithms on top of it, and then you can design data structures like heaps to implement them, okay? And then one of the coolest idea in computer science, and then take one simplest example, just use Dijkstra's algorithm on a graph to compute single source shortest path. You're gonna have extract min, decrease key, and a trace like that. You can show there will be n extract min, m decrease key, so there are different ways you can implement it. And that give you different time complexity. And if you use Bob's Fibonacci heap, it can give you even better bounds. Okay? So how about, of course, we're in a parallel world. So when we have multi-cores, we have GPUs, CPUs. What can we do? What should it be in the parallel setting? Okay, so the easiest way is we still have these operations. We let them happen all together. Okay, and that is the classic concurrent setting. So the idea is I'm going to run them together as long as the consequence is similar to linearize them in a sequential order, then I'm good. Okay? So this is simple, and then people have been studying this for decades, initiated by maybe Hurley and a lot of pioneers, and received a lot of success in the past decades. The only thing is this is a pretty hard setting. So if you work on concurrent data structure, you probably know how hard it is. If you don't know, if you haven't been working on it too much, I recommend you to watch Ares Pentrek's talks. They're very good talks, very cute animations. And then the common theme is always like something very simple in the sequential setting can be drastically very hard in the concurrent setting. For example, just knowing how many elements in the concurrent data structure. Okay, so usually with 100 CPUs, you don't normally expect 100 times speed up on concurrent data structures. You want them to finish correctly in a log-free or wait-free way. That's pretty decent. As a comparison, for parallel algorithms, if you have 100 cores, usually you're expecting, let's say, 50 times speed up. And then there was a gap here. So what makes, like what is the difference here? So I will use one example to show what we're using in parallel, what data structures we use in parallel algorithms. So here we use one example, also computing shortest path, called row stepping algorithm. It's a very simple algorithm. The details are not important, but the idea is when you compute shortest path, like Dijkstra, you have an array of tentative distances for all vertices. So instead of picking one and relax a neighbor at a time, the row stepping algorithm, you pick row elements together, extract them, relax all their neighbors together using the decreased keys, and then take another row elements and keep iterate until all vertices are finalized. Okay, so that is the algorithm. One thing you can notice that here is you have the extract min and you have the decreased key kind of running together in a parallel way. But there are clear synchronization points here. So when you're extracting keys, you're only extracting keys, and vice versa. Okay, so one thing, this is usually for correctness concern. For example, if you consider I have insert 3 and delete 3 together, and I query 3, should 3 be in my data structure? It depends on the order I process them, okay? Which is fine because if you think about your bank account, you can have withdrawn and deposited all together. And as long as they are all being processed correctly, you're good. But in an algorithm, you don't want to have a query and the answer can be either yes or no. Then what is the purpose of still doing this query, right? So the first observation is we're using this so-called batch parallel setting. That is, you have these, synchronization points at any time concurrent operations applied to the data structure are of the same type. Okay, this is mostly for the semantics. So you know what the data structure will be after the updates, and when you do the queries, you know what you're going to get. And then the batches can be explicit or implicit, but you cannot have insertions and deletions altogether in most cases, in most of the parallel algorithms. Okay, and then if we're in this setting, another observation we can have is now you have these extract, not just one min, but row smallest element. At this point, all processors are available. Okay, though they're not trying to block each other, and then like in the concurrent setting. So this is the second observation. Okay, so we are trying to design a parallel algorithm to update the data structure with a batch of elements. Okay, and not every processor is working on one insertion or one deletion at a time. So you're actually, trying to compute. You want to design an algorithm that can design a parallel algorithm that apply this batch updates all at the same time, either in a divide and conquer way, mostly, but you can do it in an iterative way or another way as you like. Okay, so, and then here you need a scheduler to map the computation to all the processors, but we have work stealing, which works well, and the operations in advance. Okay, that is another benefit you can take use of when you design parallel data structures. But this is also, it may incur some overhead. So you can have, partially have them explicit in a batch, but you can also have part of it in the concurrent setting if you're using, let's say, hash table. Then you can leave that part in a concurrent setting. That's fine. Okay, so these are all the summary, all the observations. Summary for the observations. You have the batch parallel setting. That actually makes the problem a lot easier. Okay, easier than the concurrent setting, and all processors available. So we're actually designing parallel algorithms to apply these updates or constructions. We're not trying to, to analyze how processes react together with each other. Okay, and now you're designing an algorithm. The correctness is usually trivial, and then the problem is a lot easier. And then you can try to design good algorithms with work and span bounds. You can directly plug into your entire algorithms and get overall theoretical guarantee, worst case or with high probability or whatever. Okay, and then of course there are a lot of parallel data structures. If you're old enough, you have read a lot of PRAM papers. You will see some parallel data structures there implicitly or explicitly. But one of the earliest paper I know is this interesting paper. They call it phase concurrent hash table by Julian and Guy. This is not a super complicated paper because it's about hash table, but it has a lot of interesting discussion, mostly, all of these. Okay, so if you want to design a parallel data structure, where are you looking for? And then a lot of interesting discussions. It's in SPA 14, and then after that, I don't know how many of you have known P-tree, which is probably one of the most well-known parallel data structures. That is for 1D search tree. And then there's a lot of others, and some of them I've been working on it. This is a very short list. I know a lot of you sitting in this room have contributed to some very cool ideas in parallel data structures. In today's talk, I'm only having time to talk about one of them. It is multidimensional search trees and a KD tree. But before that, let me just have a recap again. So what are we doing? We're designing a parallel data structure with these parallel algorithms. We want to explicitly answer how to maintain a data structure. For example, how to efficiently construct a binary search tree or a KD tree or whatever. And then how to efficiently batch update them. And efficient here, we mean work, span, I/O, space, all these classic measures. And also history independence. And there are several levels of history independence you can try to achieve for these parallel data structures. And not only that, another very interesting part, I don't have time to talk about it in details, but how to design the interface of parallel data structures. Again, taking priority queue as an example, sequentially you have insert, decrease key, extract min. We all know that. You can do that in a concurrent setting. But in a parallel setting, you can still have extract min, but then you can only extract one element at a time. Usually that don't give you a lot of parallelism. You can consider, extract many of them. It can be below a certain threshold. In the previous example, you want to extract rho or k elements that are smallest all at the same time. And sequentially, you also have these mergeable heap, these lazy updates, all these fancy ideas. How do they map how do they map to the parallel setting? And those are the interesting questions. And one key interesting observation is that once you slightly change the interface, the best algorithm can change by a lot. Okay, unfortunately, I don't have time to talk about this. And as I mentioned in today's talk, I'm only going to talk about the KD tree. But before that, do you have any questions? All right, so let's move on. Okay, so I'll give you one example of our design of parallel data structures, which is KD tree. Okay, so KD tree is a spatial partition data structure. Okay, usually used in 2 to 3D, but it works all the way to usually up to 10D. And if you have higher dimensions, then it won't work very well. So the high level, so most people use KD tree in this way. So you have all these points, let's say in 2 dimension. I first look at the x dimension, find the median, and then make it as the root, and then partition the space into 2 regions, left and right. And then for the left-hand side, I've picked the median, but in the other direction, in y dimension. And then I pick the median again on the right-hand side, keep doing that. And in KD tree, every internal nodes represent a sub-region like that. And then you just keep recursively building that until you either have leaf of size 1 or more realistically have nodes no more than 32, and you stop, okay, and keep it as a leaf. Okay? And KD tree is widely used. It's 50 years old, and it has 11,000 citations, more than most of us in this room. So this is a very successful data structure. Why is that? So the algorithm is fairly simple. Okay, find the median, partition, and recurse. Okay, that trivial. We know we can compute median in linear time. So that is in log n work for construction, and it's easily parallelizable. And it's simple and elegant tree structure, linear space, log base 2 of n tree heights. And it supports a wide range of queries efficiently. Like Julian talked about high dimensional space in the previous talk, but in low dimension, it just use KD tree. That will be good enough for the nearest neighbor query. Okay, so people have been using KD trees for 50 years. And then is it perfect? We realize that there are still a lot of challenges. One of them is KD tree is generally considered to be a static structure because you need the medians. Okay, so if you insert 2 points on the left-hand side, the median is no longer true. Okay, so you have to rebalance it. How can you rebalance? The simplest way is just to rebuild. Okay, so in Seagal, that is what they do. So once you insert points, they just call a rebuild. But this will be super slow. Okay, and another solution is called logarithmic method. The high-level idea is also simple, if you have not heard about it. So if you have n elements, I'm going to build up to log n trees based on the binary representation of n. So now if I insert another point, and then it will go to the first leaf. So if so first tree. If the first tree is full, I move them to the second tree. And if they're full, I just keep moving that. And you can show that every node will be moved for at least log n times. So that is better than every time. Okay, so in that way, you can make KD tree a little bit dynamic. But then the issue is now you have log n trees. So when you do the query, you need to query log n trees. So it is at least a factor of log n slower, which is significant. That is a cost, the overhead, to make the tree dynamic. Okay, so not only that, it's hard to make the tree dynamic. Even in a static setting, it's pretty interesting that we don't even know before our work how you can build a tree efficiently. Okay, so that algorithm is simple: find the median, partition, and recurse. So you can find the median in parallel, partition in parallel, and recurse in parallel. which is fine. But the only issue is that in every level, you have to run a partition as you move data around. So you shuffle it every level. So you have a tree of height log n. You have to shuffle it for log n levels. This is bad because I can tell you, if you know parallel sorting, you're going to shuffle the data every log m levels, where m is the cache size. So if you plug in the real cache size, you're only going to shuffle the data once. Okay, you have the data, you shuffle them, and they fit into cache, and everything is free. Okay, so the classic way to build a KD tree also have very large I/O cost. Okay, so what is the issue here? What would make it so hard? Okay, so we think the answer is is just because of the balancing criteria. So in the classic way, you have a fully balanced KD tree with tree height log base 2 of n. In order to achieve that, you have to find an exact median for every level. That make the computation very slow. And then you can also make the update of the tree very slow, very challenging. So our solution is also very simple. It's just a few words. Okay, so if we're making the tree exactly balanced is hard, then we can just make the tree slightly unbalanced. Okay, so this is the work in our recent Sigma paper with Ziyang, Zheqi, and Yihan. So in this paper, we show we give you two versions. Okay, the strict version and the relaxed version. For the strict version, we say, okay, the tree height, if you allow a constant additive factor, then it will still maintain all the bounds. You have the relaxed, that is on the theoretical side. On the practical side, we realize that it actually doesn't matter if the tree height is log n. We do a lot of benchmark, order of log n within a constant fraction. We do a lot of benchmarking and say that as long as the tree is not too unbalanced, then the query time is very similar. Okay, so that will be sufficient for queries in practice. In all cases, we can achieve efficient construction for work, I/O, and polylog span. That means highly parallel. And at the same time, it supports efficient batch updates. Okay, so that's the one-page takeaway. The rest of them are just some details, which are not that important. For example, for the construction, the classic way, you find the exact median, build one level at a time. In our case, if you're building one level is hard, then it's slow, then we're going to build lambda levels together with one rounds of data movement. Okay, they're going to save a lot of IOs, and we use samplings to decide the splitters. So otherwise, I don't know how you can find, every time you have to look at all the elements, and that gives you a large cost. And then once you build lambda levels, you sieve the data into all these subtrees in parallel and recurse. Okay, just with a little more technical details, we take sufficient samples. We use these samples to build lambda levels. We sieve the points, the subtrees, and recurse. And there's building the treelet, we call it, and then the sieving the points. Okay, so we have theory audience. So also in our paper, there are some theories, but I'm not going to read it. I have an illustration here. So now you want to build lambda levels, so you have 2 to the lambda. Oh, okay.
You say, I was wondering, what would you say? Yeah, you take sufficient samples. If you took just 1 point,
Okay.
Then inspired by like quicksort analysis, it would still give some kind of O of log n bound, it seems, right?
Yes, right. That will be the tree height will be log n with high probability, but the tree can be pretty skilled. So
is it actually a bad idea in practice to take? Or do you not know?
So our experiments, so we do it in this way. Okay, so basically our observation is if the balance criteria is between 10% and 90% or better, then it can be maybe a small percentage slower, like 5% slower, but that's fine. But if you go beyond that, let's say 22% versus 98%, that can be pretty bad. So if you use a tree-like structure, that's a good question. I haven't checked, but it can be bad if you have a bad random number. Or in this case, actually, it's not a tree. It's because it still find the median of some samples, so it might be slightly better. But okay, let me finish the algorithm here, and that's a very interesting question. So the algorithm is we have lambda levels, 2 to the lambda leaves, and then I put sigma samples in each subtree. So in total, I'm going to have 2 to the lambda times sigma samples here. so that this is the oversampling rate, making sure that we're not going to have very bad splitters. And then by some simple Chernoff bound, you can show if you put log n, at least log n elements here, the tree height will be log n with high probability. And by some more complicated but a high school level calculation, you can show that if you put log n to the cube elements within each leaf, the tree height will be log n plus a constant factor. Okay, and that's the strict version. And in practice, you can use this version, and that's already pretty good. That is sigma, and you also have lambda here. Lambda is log of the cache size divided by a constant factor. So that makes sure that all these computations are within the cache. And then when you sieve the points, they all fit in all the auxiliary structure fit into the cache, so they will not cause significant overhead. Okay? And the next step is to put the points into the subtrees like that. And then Ziyang find a very good online animation here, which is very cool. You have the inputs here, you have the lambda levels, and these are the subtrees. So you sieve the points, put them into the leaves, and recurse. This part is, if you know parallel algorithms, this is a standard transpose process. You can just use it as a black box. Okay, so that's the two parts here, and to put them together, we'll have a work span of I/O bounds. You can show that both the work and I/O bounds are optimal, and the same as sorting. And then we can achieve polylog span, which means the parallelism is also very good. Okay, the batch update is similar, very simple. Okay, so in the previous setting, we can either rebuild the tree every time. The tree is fully balanced, but the update is slow. If you have the log tree, a logarithmic method, you have log n trees. The update is fine, but the query is slow. So can we get them simultaneously? Yes, in our PKD tree, we can use a single tree in a weight balanced manner so that you can have fast query and fast updates. In case you don't know what weight balanced tree is, we just mentioned answering Kuba's question, it's just the two subtrees, if they don't differ by a lot, then we call it weight balanced. Okay, so you can control the imbalance ratio, and in 1D, there's a data structure just called weight balanced tree. And then if one subtree becomes too heavy, you can just rotate it and make it balanced. KD tree does not support rotations because all the nodes represent nested subregions. You cannot just rotate them around, but that's fine. We can rebuild the unbalanced part. So this one is called partial rebuild. This is proposed by Overmars in his PhD thesis, the design of dynamic data structures. You can show just rebuild the unbalanced part. And then the 1D analogy is the scapegoat tree, and then just weight balanced tree. But if you replace rotation by partial rebuild, that is the scapegoat tree. Okay, so this is similar for in our PKD tree. We just partially rebuild the part that is no longer weight balanced. Okay, for example, we have the batch insert. We just, the same as our construction algorithm, we look at lambda levels together. And then we just sieve the points to the subtrees. Part of them are still balanced. We're good with it. And some parts can be imbalanced. So our batch insertion algorithm just, in parallel, rebuild the imbalanced part and recurs on the balanced part. And that's it. I just make KD tree dynamic. Okay? So that's all the algorithms. Okay, well, I'm going to show some experiments. Okay, so if you want to build the tree, we will look at the tree construction. We compare our PKD tree with some existing baselines on 1 billion elements on uniform and scale data on different dimensions. And then we can show our algorithm is almost 1 order of magnitude faster than the classic solution, the previous baselines. There are two differences here. We take the sampling and we build lambda levels at the same time. Okay, so here we use the cool machine learning word, ablation study here. Just look at each technique one by one. So we can say, okay, we have the solution. That is our PKD tree algorithm, but the other one is we we still take sampling, but just sieve the points one level at a time. Okay, and you can say that by building and shuffling the nodes every 6 levels, you can save by a factor of 4, which makes sense. And then you can also compare the sampling. You can take the sampling out and try a classic parallel median. And then that gives you about a 2-point difference, two times difference. So if putting them together, that mostly explain why it can be almost 1 order of magnitude faster. Okay, so for the updates, we have the insertion, deletion, uniform, skilled data. And this x-axis is the batch size, y-axis is the time, but in log scale because it differs by orders of magnitude. And lower is better. It's on 1 million 3D points. You can show for batch insertion, if you just rebuild the tree, then clearly it's bad. If you know the log method, it will create these staircase shapes. And then if you use our algorithm, it's a lot faster. Same for deletion. So for deletion, you can have serial deletion, which is bad. You can rebuild, that is also bad. So deletion is almost similar. Just partial rebuild the imbalanced part and sieve it, and then you can get much better performance. Okay. So now we, as Kuba mentioned, now we have the tree that is not fully balanced. Will that sacrifice the query performance? In most cases, not. And in this talk, I'm only giving you a very simple instance. You can go to our papers for a lot of benchmarking. This is KN search, just in low dimension, high dimension. Julian talked about it. In low dimensions, you can just do this. It's a million points, 3D points. Query size 10 million. All the queries are run serial, but we run all these queries together in parallel. Okay, and then we have k equals to 1, 100, 110, and 100. Basically, the takeaway is if you have log entries, then the performance is bad. If you have just one single tree, the performance is almost similar. Okay, it's all about some implementation tricks that makes maybe one of them 20% faster than the other one, but they have similar performance. Okay, I'm mostly on time. Good. So takeaways for PKD tree. Okay, so this is a general idea to achieve parallelism and IO efficiency. You can definitely apply it to get a parallel scapegoat tree, but we have P trees already. So what can we learn from it? Okay, so one thing we noticed that is, let's say, I don't know how many of you know quad trees. So basically, you have points in 2D, just cut it into middle, and then recursively do that. And almost all classic solutions will sort these points based on the z-curves. And then once you have them sorted, you can binary search the split point and then build the subtrees recursively. That's all the existing solutions. And then once we have the PKD tree, we compare to these constructions, and we realize that storing and sorting these curves are already too slow. Okay? We do some back to the envelope calculation and realize there's no way you can make the sorting-based solution faster than PKD tree, even though PKD tree is a balanced tree with usually generally considered higher quality, unless you're doing the uniform data. So we thought about it for a few months, and we realized that we don't have to do this. So we can just use the sieving idea so that here the partition is easy. You just sieve the points into these levels, lambda levels at the same time. Okay, we can show that this is exactly the same thing as integer sort. So integer sort, you have the bins, you put the things down, and then we call this implicit integer sort. So the computation is the same as integer sort, but we don't generate the integers, so we save the overhead of generating them, computing them, and get rid of them later. Okay, so this is a very cool idea, and then I can make quad tree a lot faster. Almost faster than PKD tree in most cases. In some extreme cases, on very skilled data, they have similar performance. And there are a lot of generalizations. For example, there are R trees or BVH. It's used a lot in database and computer graphics. And then this data structure relaxes the requirement for very strict balancing criteria. So it is faster for updates and slower for queries. Okay, and one way you can build this R tree is instead now you don't use the z-curve, you use the Morton curve or Hilbert curve. Okay, and then you build an R tree, you use a 1D structure, and then 1D search tree like P-tree, and then you can get each subtree corresponding to some boxes like that. Okay? And let's try it. And we realize that we pick pack tree because that is a variant of P-tree, and then you use it to maintain 1D data. And realize that this is too slow. You map data to 1D, and you build a tree. And now you sacrifice the query performance, but you also sacrifice the update performance, and you don't get anything. And then we have, for half a year, we're saying is R-tree. R-tree has 15,000 citations, so it's even more widely used. So we're thinking if parallel R-tree is useful, and we try to understand why PKD tree is a lot faster than all these R-tree implementations, and realize the difference is that in PKD tree nodes, I've mentioned for the leaves, we take 32 elements together, but we keep them unsorted. Okay, but in a 1D ordered index, we keep the leaves sorted. And that minor difference actually give a very big, it's a constant, but a large constant difference for the performance. Okay, so if we just redo the pack tree or P tree, make the leaves unsorted, it can make it up to 8 times faster because we're not dealing with 1D data. We sacrifice the query performance a little bit, but then we can just make the construction or the updates really fast. Okay, these are some work under submission. So summary for today's talk, we talk about parallel data structures. This is a very, I believe, interesting direction. There are a lot of interesting works already, different from the classic and concurrent setting. Design goals, efficient construction and efficient updates. And of course, at the same time, sometimes you need to rethink the interface design, and sometimes the 2 dimensions can interact. And a lot of interesting questions remain to be answered. All right, it's almost on time.
Time for a couple questions.
So I have a question of the intro part. You mentioned that in the concurrent setting, algorithms tend to be slower, if I understand correctly, because that's more difficult, right? You may have query update at the same time, and so the parallel data structures work faster generally, and that kind of makes sense. Like this parallel setting is simpler. At the same time, as a non-expert, I know the concurrent union find as one of the few concurrent data structures I know, and that actually leads to the fastest possible connected components implementation, to the best of my knowledge. And I guess the reason is that we're desynchronizing because we have a concurrent algorithm. So what is the general, is this like an outlier, or is the picture a bit maybe a bit more complicated? How do the concurrent versus parallel data structures compare?
Yeah, that's a very good question. So,
Can you just summarize it?
Yeah, I've summarized it. So there are a lot of very fast, efficient concurrent data structures, union find, hash tables, and they're all pretty good. Depends on the structure. So sometimes they can also be efficient. So as I mentioned, I think I mentioned one sentence. So it can be partially in the parallel way, partially in the concurrent way. If you have a concurrent data structure, you can still directly use it. It's more like if you consider like KD trees or search trees, then the parallel ones can be usually faster, but not sure. We'll see what happens.
So this is basically what you said. It reflects the current state of our knowledge. It may mean that there is some concurrent KD tree still waiting to be discovered. Right?
That's definitely an interesting question. I think Guy has a paper cleanly installed this year. It's a concurrent KD tree. We haven't done any comparisons, but we can see. Maybe there will be a very efficient concurrent KD tree, or maybe that is already. Okay.
One more question. There is time for one. All right, let's thank the speaker again.